Hey everybody, what's going on today? We're starting lecture number 12. This is all about the standard norm curve, z-scores, and the rules calculated function out there called NormCDF. Our EQ for today is how do I use NormCDF to answer probability questions? Well, the first thing we want to do is remind ourselves about what we talked about in the last couple of lectures, and that was about the normal distribution, which is this unimodal symmetrical bell-shaped curve, and that follows a very specific distribution following the empirical rule, the 68, 95, and 99.7% rule. Also, we talked about z-scores, and z-scores are calculated as such. Z equals x minus mu over sigma. You take your individual observation, see how far away it is from the mean, and then divide by the standard deviations. What the standard normal curve does is it takes anything that's in a normal distribution and it standardizes every single value. Why is that an extremely helpful tool? We don't have to standardize every single possible value because it's already been done for us. By looking at this z-score, somebody's done like a crazy amount of calculus and found every single z-table and the area under the curve at any point. Not just at 1, 2, 3, -1, -2, -3 standard deviations, but even at 1.2, 1.37, 1.4. The standard normal curve is a hugely important thing in this course. The standard normal curve can be notated with this capital N 0, 1, saying it's normal with a mean of 0 and a standard deviation of 1. And what it's done is it's taken, again, every single value is set to the standard z-scores. So we don't have weight, we don't have height, we don't have time or anything like that on the x-axis. We have z's on the x-axis. And why this is hugely important, because by converting to a z-score, we mean that any approximately normal distribution can be modeled using this curve. Then we can use this thing called the z-table. The z-table, or the table of standard values, sometimes you'll see it listed out as table A. That's just the way the AP Statistics calls it, is table A. It's the table that gives the proportion of the area under the standard normal curve at a given z-score. And what it does is it gives the probability that a z is less than on an observed value. Well, what does that mean? What does this table actually look like? Well, let's take a look at an example to find out. So in this example, we have two students taking two different tests. Sound a little bit familiar? Well, Jennifer takes a Japanese test and scores an 80.7. So we've got Jennifer taking a test and gets an 80.7. Hans takes a French test and scores 81.3. Jennifer is adamant the Japanese is harder than French and tells Hans that her score is actually more impressive. The mean and standard deviation for these two tests are 75 and 3.5 for Japanese, respectively, and 77 and 2.5 for French, respectively. So we've got all of our information down. Let's go ahead and jot down those important parts. Maybe we can write them in the left-hand column over here just for space. So we have Jennifer, on her tests, she got an 80.7. The average score on Jennifer's tests was 75, and the standard deviation was 3.5. For Hans, he scored an 81.3. The mean score on Hans's test was 77, and the standard deviation was 2.5. So we know with those bits of given information, we know we can calculate z-scores, and maybe that's going to come in handy. But here's the next part that's important for us. The distributions for both are approximately normal. So we're going to be able to not only do more than calculate their standard score and compare the two different test takers on their different test scores, we are also going to be able to see just where exactly did they rank and what percentage of individuals scored worse than they did. Let's take a look. So the first task is obviously to see who scored better relative to their class. Well, let's go ahead and calculate their z-scores. So for Jennifer, that z-score was 80.7 minus 75 divided by 3.5. Doing a little bit of subtraction here, we have 5.7 divided by 3.5. Well, that's a gross fraction. I need my calculator to do that, so I'll go ahead and punch that into a calculator. And I'm going to get 1.63. So that's my z-score. Now you notice that doesn't fall on 1, 2, or 3 standard deviations. That makes it a little bit difficult to find those proportions that we did in the last lecture. Let's find out about Hans. So Hans, his z-score, will be 81.3 minus 77, x minus mu, all divided by sigma. That's going to be 4.3 over 2.5. Rounding to 2 decimal places, I see that this one is 1.72. So, who scored better relative to their test and their class? It was Hans. By just how much, though? By looking at z-scores, it can be kind of hard to actually see just how much better somebody did. What we can now do is we can look at their relative frequency, essentially their percentile rank. Let's go ahead and do that. So the way that we're going to do this is by looking at what's known as that z-table, or the table of standard values, and that'll help us to answer part B. What percent of students scored lower than Jennifer on her Japanese test? Okay, so since this doesn't land at 2 standard deviations or 3 standard deviations, I can't use the empirical rule. We need something else. We need something more precise. This is a cutout of the z-table, and it's a super useful tool. Let's see how to read it. You'll notice that the z-score is, or z is listed in the top left cell. The first 2 digits are going to be given in this first column. The first row gives us the final digit, or the second decimal place. If you remember, I said to round your z-scores to 2 decimal places. This is exactly why we do that, because we can start to see the z-scores being represented always as 2 decimal places. Okay, this is about as precise as we would ever care to make it. So let's take a look at Jennifer's z-score. Okay, Jennifer's z-score was 1.63. So I look at the first 2 digits, that's 1.6, and then the final digit was 3. So we look at this, and now what we want to do is we want to see what's the inside of this table. The inside of the table, the intersection here, is going to give us the proportion of students that scored worse than Jennifer. And that's 0.9484. So what does that tell me? 94.84% of all students would score worse than Jennifer. And she did pretty good. And we can write that out as the probability that a z-score is less than 1.63, which is the same as saying the probability that somebody scored worse than Jennifer, which we can say a probability that any test score is less than Jennifer's test score is equal to 0.9484. So she scored better than 94.84% of all other Japanese test takers. Now let's take a look at Hans and see what proportion of students scored lower than Hans on his French test. Okay, so Hans had a different z-score. His z-score was 1.72. So again, we look at 1.7 in that first column. The final digit is 2, so we look there, and now we look to see what is the intersection between those two. And we know that this should be a higher proportion because Hans had a higher z-score, and sure enough it is. So we can say that for Hans, the proportion of z-scores that were less than 1.72, which is the same thing as saying the proportion of students that scored worse than Hans, is equal to 0.9573. Since this one asks us specifically for proportions, I'm going to leave it at that. I realize now I forgot to include my percentage symbol there for Jennifer, but that's it. And this is how we read a z-table. One of the other things you are frequently asked to do on an AP test or on AP style questions is to actually work backwards with the z-table, which means you're going to actually be given the percentile rank rather than the official score. And you might be asked to find, well, what did the student actually score? What was the mean score, or what was the standard deviation? The idea here is you're going to work backwards to find the z-score and still use that z-score formula or the z-score relationship to find the thing you need. So let's go ahead and do that. On a test with a mean of 75 and a standard deviation of 3.5, so that was Hans's French test, or no, I'm sorry, Jennifer's Japanese test, what score would someone have to get in order to rank in the 95th percentile? So, if you look back at the previous example, Hans and Jennifer were actually extremely close, like less than a percentile off from each other, right? Well, what would somebody have to get in order to get at that 95th percentile? Let's say you get a free prize if you score in the 95th percentile, or a scholarship or something like that. Well, let's figure that out. So, in order to score in the 95th percentile, that means we want to know what value inside the table is closest to this one, 95th percentile. So, inside the table, which one is closest to 0.9500? You might not find the one that's exactly there, but we're looking inside the table. This is not a z-score. Percentiles, rankings, percentages, those are things inside the table. So looking through this one, I see 9.9495. That is the closest percentile to the 95th. Now, work backwards to see what z-score that corresponds to. Well, the first two digits are 1.6, and the last one is 0.04. So, the z-score is equal to 1.64. That's the standard score that somebody needs on this test with a mean of 75 and a standard deviation of 3.5. Okay? But what's the actual observed score? What's the score a student would have to get in order to get this test? This is the thing we don't know. We do know our mean is 75. We do know our standard deviation is 3.5. So let's plug all of those in to our z-score formula. We have 1.64 equals x minus mu over sigma. Now it's just a clever bit of algebra, right? What do we need to do? Multiply both sides by 3.5. That's going to cancel out the 3.5 on the right-hand side. 1.64 times 3.5 on the left-hand side. I'll have to punch that into a calculator. And I get 5.74 equals x minus 75. Next step is to add the 75 to both sides to get x all by itself, and we get 80.74 is equal to x. So if somebody wants to score in the 95th percentile, they will need to score at least 80.74. Usually a score like that's going to be rounded up to 81 or maybe just 80.8. You know, if we're going to one decimal, to get into at least the 95th percentile, we would need to round up no matter what. So even if you don't have exactly the things you're thinking about or what's isolated in your z-score formula, you can still use algebra to reconnect and restructure that formula to find the thing you need. Working backwards is very common. Alright, let's take now a look at some more in-depth examples that really get some more practice working with calculating that z-score and utilizing the z-table. So, IQs are based on the normal distribution, where we have an N116. Remember, what that tells us is that the mean is 16 and the standard the mean is 100 and the standard deviation is 16. That describes our IQ scores. What proportion of people's IQs would you expect to be blank? Let's go ahead and answer some questions. Zoom in because we want to draw lots of pictures here, okay? And I need plenty of room. So we're going to do these first 4 questions the long way, and then we'll try and use a calculator to speed things up. One thing that is consistent that I always want to make sure you guys do, draw a picture every time, okay? Get used to drawing your normal curve. Now, you don't have to mark every one of those standard deviations and input every 34%, 13.5%. Don't do that. Put your mean, write out your standard deviation, and your cutoffs. That's what we want to do. So, with this one, we will draw out our normal curve. It definitely does not have to be perfect, okay? Just a rough idea for a sketch. The mean is 100. Now, we want scores that are over 80. So any score that's going to be over 80, well, 80 I know is to the left of 100. So that's going to be somewhere over here. And I'm going to draw my cutoff. I'm going to actually slice right through my normal curve. But we want over 80. So what side do we want to shade? We want to shade the right-hand side. So this is what we're looking at. What is this area? Because the area under the normal curve, under a certain region, is going to give us the proportion of individuals that fit that description. So we find this area, we will find this probability. And we know we can do that by calculating a z-score. So z is going to equal 80 minus 100 divided by 16. Again, this is just our x minus mu over sigma. Calculating that z-score, we get 80 minus 16. That's going to be, what, negative 20? And negative 20 divided by 16, negative 1.25. Okay, so we have a z-score of negative 1.25, but that on its own does not tell us what our proportion is. What we need to now do is look at the full-on z table. So let's go ahead and do that. So notice that there are two sides to any z-table. There's the positive side with all of our positive z-scores, and it's going to extend all the way down to 3.49, because that's going to accommodate 100%, almost virtually all of our individuals in a population. But we have z-scores that are also negative, just like we saw now. The second page of your z-table is going to be, or the first page, excuse me, is going to be your negative side of your z-table. Now, a couple of things to note. The z-table, again, always gives you area to the left. Every single time gives you area to the left. Can't stress this enough. Every single time, the z-table gives you area to the left. So let's find our z-score. Our z-score was negative 1.25. So we'll use our highlighter and mark negative 1.25 on our z-score. Negative 1.2, and then 5 for the second decimal. And you're looking for the intersection between those two, and it's this, 0.1056. You can see pretty clearly that's the intersection between those two. So that tells me that 10.56% of all individuals will have an IQ below 80. Let's go back to our example and fill that in. This is 0.1056, but that's area to the left. Is that what we shaded? No. We shaded everything to the right. So what do we need to do? Well, this is a complement rule, right? If 10.56% all have an IQ below 80, then what about those that have it above 80? Well, all we got to do is subtract. 1 minus 0.1056 will give us the answer we want, and that's 0.8944. And that certainly does appear to be about 89.44% of that curve. I can at very least see that it's more than 50%. Let's take a look at the next example. Our next example wants to find any IQ that's under 90. Well, it's the same distribution. It's still approximately normal, with a mean of 100 and a standard deviation of 16. We always like to write out our standard deviation. That's always helpful. Now, the individual in question is going to be somebody that scores under 90. So 90 is less than 100. It's to the left-hand side. Draw my cutoff. Under 90 means I'm looking everything to the left. And that's going to be this space. This is what we want to know. What is the area under the curve to the left of 90? Same process. Calculate your z-score. This is something you can punch into a calculator in just one step. You don't have to try and be like a super brain wizard and do everything by hand. use your calculators. They are helpful. Round it to 2 decimal places, negative 0.63. For you notation nerds, what we're actually looking at here is we want to know what's the probability that any z-score is less than negative 0.63, right? Because we're looking at those that are under 90 or to the left of 90. Okay, so we go back to our z-table. On our z-table, we'll erase the highlights we made, and we look for negative 0.6. 3 is our second digit. The intersection between those two rows and columns is 0.2643. Again, you always maybe wondered, why am I always rounding my proportions to 4 decimals? This is why. We use NormCDF a ton, and we use the z-table a ton, and the z-table consistently will round things to 4 decimal places. That's about the consistent level of precision. So 0.2643 is that area to the left of the curve. So we'll go back and we'll mark that area as 0.2643. That's the area to the left of the curve. Do we need to subtract from 1 this time? No, because we wanted the area to the left of the curve. So that's our answer, 0.2643. Boom, boom, boom. Done and done. The next example here is going to be quite a bit more involved, so let's take a look at it. We now want to find an IQ that is between 112 and 132. What's the probability that a randomly selected individual we pull off the street has an IQ between 112 and 132? If it's truly random, we can use this same process. So we have 100, and then our cutoff will be above the mean. Oh, that's different. And then another cutoff. Wait, how are we going to work with 2 cutoffs? It's the same thing that we had done before. Okay, what we are really looking for is what's the probability that any randomly selected person will have an IQ that is in between 112 and 132. So with 2 cutoffs, we want to shade this inside part here. This is what we want to know. Well, how am I supposed to work with this? First thing you need to do, find the z-score, but you got to do it twice. You got to do it for each one. So we'll find first the z-score at 112. I'll go through this quickly. Now our z-score at 132. So we got 2 z-scores. Well, what we can do is, knowing that our z-table is going to give us the proportion of everything to the left of a certain mark, what we can first do is find what's the proportion of everything to the left of 132. Then we'll find everything to the left of 112. When we subtract those 2 proportions, those 2 areas, what are we going to be left with? Everything that's in red. Okay, so what we want to do, go back to our z-table. The first z-score that we need to find was 2.00, but it's positive. So we go to our positive side of the z-table, 2.00, and that's 0.9772. Now we stay on the positive side because our second z-score was 0.75. So here's 0.75, and the intersection there is 0.7734. Well, let's go ahead and subtract those 2 values back on our page, 0.9772 and 0.7734. And when we subtract these, we should end up with what? This is going to be 2038. You can double check my math and ridicule me in class if I got it wrong, but I think my mental math holds up there. 0.2038. And that's the area that we shaded. And that's our answer. Simple as that. So if you really wanted to write out the notation, you could do so as such. Probability, again, that somebody scored between 112 and 132, or your z-score is between 0.75 is less than z is less than 2.00. Do you need to show this notation? Absolutely not. Notation is not a requirement generally, but it is good communication. All right, last example for this one, and we'll do the rest in class. We want to know what IQ represents the 15th percentile. So critical reading is huge here. Is this giving us an IQ? No. It wants to know what IQ. That's what we want to find. We want to find X, the IQ of a randomly selected individual. What we're given is a percentile, and that percentile is what is inside the table. So what this should tell you is this is a lot like the one we did at the very top of this page. It's the same kind of question. Let's make sure we draw our picture and we know exactly how to actually structure this, okay? So we draw our x-axis and our normal curve, put our mean in the middle. Again, I keep forgetting to add my sigma of 16. It's a good habit to get into. What we want to find is the 15th percentile. So the 15th percentile, is that more than 50% or less than 50%? It is less than 50%. So what does that tell me? Left hand or right hand side? That's going to tell me left hand side. So put some mark. I don't care where it is. It doesn't matter. Okay? But we want to know that this area is the 15th percentile. How do we write that? 0.1500. Again, a decimal that is 4 digits long. What we want to know is our cutoff. So this is what we call an inverse normal kind of problem because we are working backwards from the z table. Okay? So the first thing we need to do is go to our z table, and we need to look inside the table now. The question is, which side do I look at? Do I look at the positive side or do I look at the negative side? Well, when I look at the positive side, I see my largest was 0.9998 and my smallest was 0.5000. So that's all the right-hand side stuff. We don't want that. We want the negative side. The negative side of the table goes from 0.003 to 0.4641 at the top and bottom respectively. We need to find 0.1500 inside the table. 0.1500 inside the table takes a moment. And here it is, 0.1492. Why not 0.1515? Well, 0.1492, that's only 0.0008 away. Okay, so that's going to be the one that we want. Work backwards. What's your z that corresponds with it? Negative 1.04. That's our z-score. Let's go back and try and put this together. So this is not x. This is z. What do we know? We know mu, and we know sigma. We don't know x. That's what we want to find. X minus mu is 100. Sigma is 16. Multiply both sides by 16, and then you're going to add 100. Try to do this all in one step. Try to do the algebra bits in your head and just turn to your calculator to do it. So we know we need to multiply by that denominator and then add the mean. Okay, multiply by the standard deviation, add the mean, and we will get 83.36 for the IQ. That is the 15th percentile, which means anybody with an IQ of 83.36 will have a higher IQ than only 15% of the rest of the population. Alright, so that's it. What we're going to work on in class is more and more practice with this, and we're going to focus on how to use the calculators. Alright? Thanks so much for watching, you guys. Have a wonderful day, and I'll see you next time.